Okay, super. So our next speaker for this afternoon is Tom Goldstein from the University of Maryland. And we all look forward to hear more about adversarial examples and thinking systems.
Sure.
Now we lost
One
your
second.
screen, Tom.
One more thing I have to set up here. I apologize. Okay, now we're ready to go.
Okay.
Okay, I'm good.
Excellent. Yay. Then go.
Okay, let's go. All right. Sorry for the delays, everybody. Thank you very much for hosting me, Carola. All right, since I'll get on the road here, since I think we're running a little behind. So I'm going to talk about a few different topics today. The main topic of my paper is going to be about thinking systems, but since some of the other work that I'm doing related to adversarial examples is also related to inverse problems, I thought I would try to sort of mash the two together, and I'll talk a little bit about some of the work we're doing on adversarial examples, and then I'll switch over and talk about some of the newer stuff we're doing with thinking systems. So these are the two topics I want to speak about. I actually think both of them are related to inverse problems in interesting ways. The adversarial example stuff, maybe the relationship isn't quite so clear, but I'll explain why I think it is related. And then I'll talk about how unrolled neural networks stuff, very closely related to what Becca was just speaking about in her talk, can be used to solve various kinds of planning problems and be able to create systems that tolerate certain kinds of domain shifts, and we call those thinking systems. Okay, so to begin with, what is an adversarial example? I think an adversarial example is a really interesting example of a solution to an inverse problem, where you essentially have a neural network that accepts an image as an input, and that network produces an output like a one-tot label vector. And you want to solve a problem that says, how do I have to manipulate this image in order to change the output of the system? It's sort of an inverse problem in the sense that you want to figure out what input image will generate this the output that is desired. Maybe I want to change the output so that it thinks this image is a car instead of a grumpy cat. And you're basically solving an inverse problem to reconstruct that image. And there actually are a lot of interesting conceptual relationships to inverse problems. One in particular is that if you're using a convolutional neural network, then you're basically doing a deconvolution to solve this inverse problem. I want to figure out what input I need to make to the convolutional layers in this network in order to recover a particular output. And everyone who works on inverse problems in imaging is probably familiar with the fact that these problems are very poorly conditioned. And oftentimes you get really bizarre and uninterpretable results when you try to do this kind of image inversion, unless you use very specific regularizers. And then you can produce examples like this, where very uninterpretable and strange perturbations to an image will change this Egyptian cat. According to Resonant 50, this is a 28% Egyptian cat, and this is a 97% traffic light. Okay, so a lot of you have seen these kinds of adversarial examples before, but one of the questions I'm interested in is what now? What can we use these kind of unstable inversion behaviors to do outside of just conventional adversarial attacks and defenses? And one thing that I'm really interested in is these sorts of applications to data set privacy. So as an example of these sorts of data set privacy applications, there are all sorts of websites that basically host all of your private information and make a lot of it available online. And then oftentimes that gets scraped by organizations that you might not be so thrilled about. I think one of the, an organization that gets a lot of flack for this sort of thing is actually Facebook. But strangely, I actually think LinkedIn is one of the worst offenders in this space, and oftentimes is not very much discussed. But LinkedIn will give your name, your photo, and your rough location to pretty much anyone that wants to scrape that information, oftentimes without even necessarily logging in. And a lot of this sort of information has been scraped by a number of different companies. I think, Clearview AI, you may have heard of, is sort of a high-profile example of this. But actually, there's a lot of I think there's a lot of companies now that are doing similar things. But basically what Clearview does is it scrapes your personal information from various kinds of social media websites, and then it sells your visual identity. So it scrapes your image, and then it maps that to both the name and also the location that you live. And then it uses that information to do face identification for various organizations, private companies, political organizations, including some organizations that have been identified, the pretty extreme political groups that they work with. law enforcement agencies that may or may not be using these services in a way that is legal or compliant with various data collection regulations, and then also foreign governments. Actually, Clearview, interestingly, has denied numerous times that they sell these face recognition services. They sell identities for Americans to foreign governments, but there was a New York Times expose on this last year that actually there's a big leak basically that showed that actually they do sell this information to foreign governments, even though they've denied it numerous times publicly. So anyway, an interesting question related to the sort of data scraping is there a way to poison data sets so that they're effectively useless if they're scraped? Is there something that we can do that makes it really difficult for people to scrape useful information for training neural networks off of these kinds of websites? Because oftentimes there are data sets that you would like to be able to host. You would like to be able to host, photos of your employees or satellite images or other kinds of images without necessarily having them be scraped and then used for machine learning purposes. So one way that you can actually address this question is how to make a data set useless if it's scraped is you can actually use adversarial examples. So here's an example of how you might do something like this, really is sort of a conceptual warm-up to kind of understand how you would do something like this. So let's say that you train a neural network. It'll have some decision boundaries. So in this case, let's say that we have a neural network that's trained on cats and frogs, and it's going to classify the two. So all the cats live in some region of RN, we'll call that catland. All the frogs live in Frogville, which is a different region of RN. And the cats are on this side of the decision boundary, and the frog images are on this side of the decision boundary. So what I'll do now is I'll make an adversarial perturbation. So what I'll do is I'll make a small perturbation to these images that scooches them over the decision boundary. And I've added some fuzz so you can tell that these are supposed to be the adversarial examples, although in practice, it'll be much more difficult to tell that these are adversarial examples, but I want you to be able to see which ones are which. So what I'm going to do is I'll make a small perturbation to this image so that according to ResNet 50, this image now lies in catland, even though it looks to a person like it's a frog. Then I'll take this cat and I'll make an adversarial perturbation to scooch this cat over the decision boundary. And now to a person, it looks like a cat, but to ResNet 50, this looks like a frog, right? So both of these images swapped over the sides of the decision boundary. And now I ask this question, if I want to train on these images, so let's say that I put these adversarial images in the training data set, what label should I put on them? Now you might think this looks like a frog, so you should probably label it as a frog. This looks like a cat, so you might want to label this as a cat. But in practice, that isn't actually the label that you want. It turns out that you want the original labels that were given by ResNet 50. So if you're going to train on this data, you want this image to be labeled as a cat, and you want this image to be labeled as a frog. And here's why you want that to be the case. It's because of distillation behavior. So when you sample this point, this is an XY pair. The X is your frog image and the Y is the label cat. That is a point on the function that was implemented by ResNet 50. I took this label from ResNet 50. And likewise, this is also this image label pair is also a point of the function implemented by ResNet 50. Now, if you train on enough of these data points, these points sampled from the ResNet 50 function, what's called distillation behavior will happen, which means that when you train on these labels given by ResNet 50, train on all of these XY pairs sampled from the function implemented by ResNet 50, you get back the exact same function. So you train on a whole bunch of these adversarial examples that to a human appear to have the wrong label, but because you're training on the labels produced by ResNet 50, you basically get the same function back when you try to do this regression again. We try to fit your model a second time. And interestingly, if you try to give these images the human labels, so if I label this as cat and I label this as frog, I'll actually get back much lower accuracy than I would have gotten if I had trained on what to a human would appear to be the wrong labels. Right. So if I train on, interestingly, if I train on these adversarial examples, so I train on images where everything to a human appears to be labeled wrong. So this is labeled as a cat, this is labeled as a frog. And here's the confusion matrix that I get. And we find that most classes in CFAR, you see this diagonal, the sort of bright band is occurring because most of the images in CFAR are actually classified correctly, even though to a human, none of the training images were labeled correctly. To a human, training images are labeled like this. So you look at them and you say, well, they're all labeled wrong. But to ResNet 50, it looks at these images and it thinks that they're labeled correctly, because when it sees this image, it sees cat features, and when it looks at this image, it sees frog features. So it learns how to classify everything correctly, even though to a human, everything is labeled wrong. And here's some examples of those wrongly labeled images that I trained on. There's this image, so everything's kind of fuzzy when it's in the CFAR data set. We'll see an ImageNet example later. But this is labeled as a cat, and it trains on images that look like this. To a human, you would say, well, that's definitely supposed to be a frog in the CFAR data set, right? It's pretty clear, this image, but it's labeled as a cat. And it turns out that this is the label you want to train on if you want to get good performance with a neural network. Here's the original image before the perturbation. This is the base image. If you train on this image and you want good model performance, you should label this as a frog. This is the perturbed image. If you want good model performance, you should label this as a cat. So what's interesting here is that there's this sort of discrepancy between the labels, between what label a human thinks is correct and what label a machine thinks is correct. This image is labeled wrong according to a human, but right according to a computer. And you can have this disparity where the correct label really depends on whether you're a human or a machine. Right? So how do we use this kind of behavior to make untrainable data? So I want to make an untrainable image, an ImageNet that if you scrape these images and you train on all of them, even if you have what you think are the correct labels, a machine will completely fail to train on that data. And the way that I'll do that, well, the easiest way to make a data set untrainable would be just to randomize the labels. So I took ImageNet data set and I just assigned random labels to everything, and then I try to train on it. Now there's no useful information in the labels anymore. And so it's not possible to train on that. Unfortunately, it's not so easy to control the label function. So if someone is hosting, say, face images on their website, right, they want to actually put the correct identity of people on those images. Similarly, you might have just a situation where someone scrapes a bunch of images and then sends them off to Mechanical Turk to get labeled, which is how many large-scale data sets are created these days, and you don't have control over the label function. So what I would like to do is I want to create a data set where everything is labeled wrong, but I don't have the luxury of having everything labeled wrong according to a human. I need the labels to be correct according to a human. I want the labels to be wrong according to a computer, so that when a computer trains on these images, it's as if all of the labels are junk, even though when a human looks at these images, everything appears to be correct. And here's how we'll do that. So I just showed this simple example where I took these adversarial perturbed images, and I wanted to put the label on them that we need in order to get good model performance. So to get good model performance, you have to put the label on them that ResNet 50 would put on them. So this looks like a frog to you and me. It's labeled as a cat. This looks like a cat, but I labeled it as a frog. And these, according to a machine, are the correct labels. So in this example that I showed before, you have these images that are labeled correctly according to a machine, but incorrectly according to a human. And so what I'm going to do is I'm just going to flip those labels. I'm going to take this adversarial example and label it as a cat, and I'll take this and label it as a frog. Now, to a human, everything seems fine. All the labels are correct. But according to a machine, so according to something like ResNet 50, all the labels are wrong. So if you train on this data, it behaves as if it's training on data where all the labels have been flipped. So here's an example of this from ImageNet. Right, I said with ImageNet, images are much more clear and it's much more difficult to see adversarial perturbations. This is an example of something that is labeled as a hen. And then in our adversarial perturbation, we scooch the image over into a semantically related but different class. So we made an adversarial perturbation so that ResNet 50 thinks that this is an ostrich. So when a human looks at this, they think it's a hen. And if you label it as a hen, they think it's labeled correctly. When a computer looks at this, they see ostrich features. And if you label this as a hen, that's very confusing to a computer. Training on this labeled as a hen, or sorry, training on this labeled as a hen is incorrect for a computer, and it will cause a degradation to model performance. So here's an example of this. This is on ImageNet. So if you train a ResNet 18 on the original ImageNet data set using a fairly standard training routine, you'll get 67% top one accuracy on clean images. But if you train on these adversarially perturbed images, so images that appear to be labeled correctly to a human and that look totally normal to a human, most of these images don't look like they're manipulated. So they look like this, right? You can't really see that this image has been manipulated. But if you train on images like this, you'll only get 1.5% accuracy if you train ResNet 18. And interestingly, it actually doesn't really matter so much the architecture that you train. So this is a CFAR10 experiment, just because it's easier to work with CFAR10. We can train a bit faster on our meager academic GPU cluster. So we crafted these adversarial attacks using ResNet 18, and then we test against different architectures. So if you train a ResNet 18 using a good training loop on the original CFAR10 data set, you can get 95% test accuracy. If you train on these adversarial examples, so tiny perturbations to the images, and they still appear to be labeled correctly to a human, so a human wouldn't notice anything fishy about this data set. If you train a ResNet 18 on this data set, you get back only 6% accuracy. And keep in mind, 10% accuracy is a random guess in this case, because there's only 10 classes. So we can actually force the network to get back worse than a random guess. You'd be better off just randomly initializing your data set, randomly initializing your network, than you would be training on these images. If we switch architectures, so now we craft the adversarial examples with ResNet 18, but I don't know what architecture is being used by the victim here. And so on ResNet 18, craft with ResNet 18, but then it turns out that the victim is using a VGG19 model, unknown to me. They still only get back 11% accuracy, slightly better than a random guess. If they use GooglyNet, which is a very different multi-branch architecture, they get back 7%, so worse than a random guess. And if they use MobileNet, they get back 6%, also worse than a random guess. So these kinds of adversarial attack methods can actually really seriously degrade the performance of these kinds of models. Okay, so moving on to some different kinds of applications. I want to talk more about these sort of thinking systems. So as I mentioned at the beginning, these thinking systems are really inspired by the unrolled neural networks that people use, essentially to learn algorithms. So you want to learn a reconstruction algorithm, for example, like for backward splitting or an ADMM method. In the last talk by Rebecca Willett, we heard a lot about these kinds of methods. And so what we do is we unroll a neural network, and then we try to learn the steps of an algorithm using this kind of an unrolled system. But what we're interested in is whether we can build systems using these kinds of methods from the inverse problems literature, basically to build what I would call thinking systems that can sort of bridge the gap between human and machine performance on certain kinds of tasks. So what do I mean by thinking? Well, in a classical computational theory of mind, the mind basically has a few different parts, but two of the key parts are this working memory and the central executive. So a basic model of a human thinking process is that you have some sort of logical reasoning task you want to solve, like solving a maze, or maybe you want to prove a theorem. And so we represent that, we form a representation of that problem in our memory, and there's a space called working memory. And then there's something called, it's in the classical theories of mind, this is called the central executive. It's basically the rest of your brain that's doing all of the manipulations other than just storing information. And the central executive basically manipulates that working memory representation. So it manipulates the representation of the problem in your mind until you're done solving the problem. And as a result of these kinds of thinking processes that we have, humans really behave differently than machines in a lot of ways. One of those ways is that humans have reasoning skills that scale up to potentially unbounded tasks of potentially unbounded difficulty. So let's say that I ask you to solve an easy theorem. You can solve that theorem, and you'll solve it very quickly. If I ask you to prove a really difficult theorem, you might still be able to prove that theorem, but you're going to have to think for a lot longer. And so just by applying the mechanisms you have in your mind, for a longer period of time, you're able to work your way toward a solution, and that allows you to scale to problems of potentially unbounded difficulty. It's not clear that there's necessarily a bound on the difficulty of theorems that a human is able to prove. We also handle domain shifts well, and that's oftentimes because we can identify causal factors, at least in visual problems, but also interestingly for logical reasoning problems, we can train on easy problems, right? So you might read a textbook with a bunch of exercises in it and learn how to solve a bunch of easy math problems. And then if I throw at you a more difficult math problem, you might be able to solve that anyway, just by basically bridging the gap between these sort of simpler problems and these more harder problems by stitching together more complicated strategies that consist of the parts, the strategy components that you learned by training on easy problem instances. And then we use this kind of thinking process. We also use to synthesize complex strategies from simple rules, right? So an example of this would be something like playing chess. So computers, if you try to teach a machine to play chess, they have to play literally billions of chess games before they become strong chess players. Whereas a human could become a pretty competent chess player using only, say, 100 chess games. And actually, world-class chess players have probably only played tens of thousands of chess games in their lifetimes, which is a tiny, tiny amount of learning for a computer system. And one of the reasons for this discrepancy is that computers generally learn by trial and error. A reinforcement learning system would learn by an exploration process where they might make random trials of different strategies and then acquire feedback, whereas a human can learn by synthesizing complicated strategies. We learn simple strategies by playing as a weak player and making mistakes, and then we can think. So by thinking over time, we can synthesize these sort of strategies together into more complicated strategies and become a much more powerful player with very, very low sample complexity. So the basic question that I want to ask is, can you learn this kind of sequential and temporal thinking behavior in an end-to-end way with a neural network? Now, it's not that humans can't it's not that computers cannot achieve this sort of scalability where you have easy problem instances and you scale up to really hard problem instances. But generally, we achieve that scalability through classical algorithms. So if you wanted to play chess, we have handcrafted algorithms like Monte Carlo tree search that we use to solve those kinds of problems. And these kinds of algorithms scale to problems of arbitrary complexity. For example, if you want to solve mazes, I can code up a depth first search, and I can run that depth first search, and it will solve problems of arbitrary complexity. I just have to run it for longer, right? So in some sense, if you let the machine think for longer, it can solve harder problems. And so algorithms can achieve this sort of behavior, but I don't want to rely on handcrafted algorithms. I would like to be able to learn algorithmic behavior end to end. I would like the system to be able to synthesize its own algorithms from scratch, and I want those algorithms to be scalable. So in other words, I would like to create a system that can solve more complex problems than it ever trained on just by thinking for longer and basically scaling this sort of algorithmic behavior to more complicated problems. And we can do that just by essentially taking the brain out of this thinking model and just replacing it with the central executive with a neural network block. So we'll actually replace this with a ResNet block that contains 2 conv layers. And our neural architectures will have an embedding unit that takes an input problem and embeds it into working memory. And then we have this central executive that's going to pick up that representation from working memory, manipulate it, put it back down, then pick it up, manipulate it, put it back down. And so what we're essentially doing is an unrolling process similar to what people do learning algorithms for inverse problems. So the basic thing that we need to do to get started with these kinds of systems is we need to be able to take the various kinds of machine learning problems, right? Image classification, maze solving, chess, these kinds of things. But these problems are typically solved with feed-forward neural networks, things like standard convolutional networks, where every layer of the network is different. We need to replace that with recurrence. And so what we do is we just use an unrolled neural network. So in a classical feed-forward model, you have a unique set of network parameters for every layer in the network. Whereas in a recurrent model, you have an embedding layer, A, that takes the input and creates a feature map. Then we just apply the same convolutional layer over and over again. So basically let it think numerous times, or it applies B, 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 until you get to the end of the network, and then there will be one last layer that extracts a solution from that working memory, and then a fully connected layer that makes that into a classification output. So one of the interesting things we found is that, and I find this behavior quite interesting, there's an uncanny similarity between recurrence and depth. So uncanny, in fact, that my student Avi wrote a paper called The Uncanny Similarity Between Recurrence and Depth. And interestingly, so this is on CFAR 10. If you train networks of different depths, so this is depth of the network on the x-axis and accuracy on the y-axis, and we look at different kinds of architectures. So for example, this kind of S-shaped curve here is for multi-layer perceptron, so just standard fully connected networks. And what we find is that regardless of whether we use we use standard feed-forward behavior, which is in blue, or we use a recurrent network with the same architecture, but the same parameters at every single layer, you get the same kind of relationship between depth and performance. So you see the same kind of S-shaped curve here and the same kind of arc curve here. This is for a simple VGG-like convnet. This is the pattern that we see for ResNet 18. So you see the same kinds of behaviors regardless of whether you use recurrence or depth. So it actually seems like we can take a lot of standard architectures and just swap out depth for recurrence. We can just recycle all the parameters, and there isn't much of a performance degradation. This is on the MNIST data set, EMNIST, so more difficult than the original MNIST data set. And we see the same sort of trends again. So if we use a standard MLP, we see that performance falls off with depth. We get the same trend regardless of whether we use recurrence or feed-forward architecture. And then this is with a simple ComNet. And interestingly, this is very non-monotonic behavior. The accuracy goes up and then down and back up again. And we see the same trend whether we use recurrence or whether we use feed-forward computation. Here's an example with ImageNet. You see similar kinds of trends in ImageNet. We just don't have the capability of running as many experiments with as many architectures. And so this is an example using ResNet with ImageNet. And you can actually, even with a complicated problem like ImageNet, you can just swap out the feed-forward behavior with recurrence. We're using the exact same parameters on every single layer, and there's not a really big difference in performance when you do that. We can also visualize this is visualizing the features. So we try to create an image that activates the features at different layers in the network. And what we find is that at early layers in the network, I actually have a zoomed in slide for this. So this is a recurrent architecture over here. At early layers in the network, you get what are basically these sort of edge detectors. At deeper layers in the network, you get these sorts of textures. And then at still deeper layers in the network, you get basically parts of objects. So you'll see there's what looks like what looks like plants in this image. You get a bunch of eyeballs in this image, so parts of faces. And then these are features that we reconstructed from neurons in a standard feed-forward architecture for ImageNet. And you'll see that you get the exact same kinds of patterns and behaviors. It really doesn't matter whether you have unique parameters at every layer or whether you just recycle them. Okay, so we have this interesting tool. We can replace feed-forward behavior with recurrence in a lot of standard problems. And now the question we'd like to ask is, can you extrapolate the performance of these networks with thinking? So the nice thing about swapping out feed-forward behavior for recurrence is that a feed-forward architecture, I have no way of extending its cognitive abilities, right? A person, you train it on easy test problems, so easy math problems, then you ask it to solve a harder math problem. A person will extrapolate, but they have to think longer in order to do it. Something like a ResNet 18, it can't think for longer. It has 18 unique convolutional layers. And once you've applied the 18th layer, there's no more layers to apply. You can't extend its abilities after it's been trained. Whereas a recurrent network, you can. So if you had all of those layers had identical parameters, because we're using recurrence, once you got to the 18th layer, you could just keep going. You could just apply the recurrence over and over again and see if you get to some sort of nice fixed point where you're able to solve more complex problems than you were able to solve during training. And so the first test problem we're going to look at, you're going to have to walk before you can run. So let's look at a really simple problem. So let's look at computing prefix sums. So this is a problem where I give you an input sequence of binary numbers, and then the output sequence that you need to generate is the cumulative sum of the input sequence mod 2. So this is a problem where you're just computing a simple cumulative sum and then computing mod 2, and then that should generate this output target. So what I'll do is I'll train neural networks to generate these outputs from these inputs. And after the network is trained on short inputs, I can then test it on longer inputs and see if it's able to make this generalization leap. So in our original paper on these thinking systems, this is the performance numbers that we had. We would have improved them quite a bit. But so these horizontal lines, so the x-axis here is depth. These horizontal lines are the feed-forward systems. They actually can't train their depth. That's why they're flat. We just support the best feed-forward performance we're able to get on any feed-forward model we trained. These red lines are 40-bit data, or on 44-bit data. The purple lines on 40-bit data. And this system was trained on 32-bit data. So essentially, we train on smaller, easier problem instances. It only ever trained on 32-bit problems. Then we see whether it can generalize to 40 and 44-bit problems. And then this performance here is in the training regime. So during training time, the network was only ever able to use 10 iterations. And if we use 10 iterations at test time, we get very low test accuracy. But if you then let it think for longer, so we let it continue past the 10 iterations that it was allowed during training, suddenly the performance increases and we're able to get nearly 100%, even though there's a pretty severe domain shift going from small, simpler problems to larger, more complicated problems. And then this is sort of hot off the presses result from earlier last week. By just doing some architecture searching, we can really blow this behavior up. So this is an example where we train on 32-bit problems and we tested on 512-bit problems, so a lot bigger. And once again, we train using only 20 iterations, and then we test using very large numbers of iterations. So this is testing up to 400 iterations. And what we see is that the feed-forward network just can't solve these problems. This green line at the very bottom is feed-forward. It gets basically 0% on any of these problems. The domain shift between 32 and 512 bits is just too severe. But these thinking systems, they also suffer. You'll see they get nearly 0% accuracy in the training regime. So if you only allow them to have the 20 iterations that they trained on, but to solve these really complex problems, they totally fail. And yet, if you let them think for longer, they'll suddenly succeed and get nearly 100% accuracy. This is an example showing the solutions we can pull out after different numbers of thoughts, so at different iterations, and you'll see that because they're doing cumulative sums from top to bottom, it resolves the earlier results first, and then it takes longer to resolve the later bits in the output sequence. Okay, so that's an easy problem, right? Just solving these sort of prefix sum problems, that seems quite simple. Let's try to jump to something more difficult. So let's look at procedurally generated mazes. So if I take these mazes that are generated using an automated process, the nice thing about mazes is that I can scale how big they are, and I can scale how long the solution paths are, and I can basically create easy mazes, and I can create hard mazes, and I can study this generalization leap, whether problems trained on easy mazes can then suddenly solve more difficult mazes if you let them think longer at test time. And interestingly, if you make small, medium, and large mazes, so small mazes here is in blue, this is a 9x9 maze, and then 11x11, and large in this case is just 13x13. We'll look at much bigger mazes in a bit. But what we see is that the path length, the average path length in the maze increases as the maze gets larger. So the length of the path that you need to identify to solve the maze is a histogram of path lengths. And we see that histogram extends to longer path lengths when we have larger mazes. No big surprise. We can also validate that the depth of a network you need to solve larger mazes is more. And you would expect that, right? A larger maze would require more sequential logical thinking to solve. And so to solve a larger maze, you need deeper networks. So this is not doing any sort of extrapolation. We're not necessarily looking at this sort of thinking behavior. These are just simple feed-forward and recurrent models that were trained and tested on the same data set. And what we find is that with small mazes, we can get over 90% accuracy using only 20 layers. But for large mazes, we need 36 layers to get that accuracy. So essentially what we see is that to solve these larger problems with more logical depth, you're going to need a deeper network. The question, though, is can we extrapolate? Can we train something only on small networks with very few iterations and then get it to extrapolate and solve these kinds of really hard problems? So what happens when these sort of systems think for longer? This is a slide from our original paper. And we find that if we train on small mazes, and small in this case just meant 9x9, and we test on 13x13, a feed-forward neural network, that's the horizontal line here, does fairly poorly. It gets about 25% accuracy on the hard mazes, where we get much higher accuracy with one of these thinking systems in the training regime. So if we test it on hard mazes, but we only give it that 20 iterations that it saw at train time, we can then unroll and we can extrapolate, and it can actually solve harder problems if we let it think for longer. And once again, I said we're doing some architecture searching. This is also one of our hot off the presses results. So this is training on 9x9 mazes and testing on 33x33. And what we see is that, so feed-forward architecture is in green. Feed-forward architecture just completely fails. It can't solve mazes that large. And if we have a recurrent architecture, it also fails. So if we train the recurrent architecture using 30 iterations on small mazes, and then we try to test it using 30 iterations on large mazes, it totally fails. But then if we let it run for longer, so we let it think for longer, suddenly it can extrapolate and it gets back to nearly 100% accuracy, even though it's solving problems that are not in the training domain. Just to give you some sense of how difficult that domain generalization is. So how difficult is it to make that logical leap? This is a 9x9 maze. This is what we trained on. And I find that with 9x9 mazes, I can always solve these problems immediately just by looking at them. It doesn't really take me any effort to solve them. In this case, the solution looks like this. It's a very short solution path. You want to get from the green, this is the start point, to the red, this is the end point. And also in small mazes, if 2 points are nearby, if you have the start and the end point are close together, the solution path is generally very small. But this is what we test. We only train on these 9x9 mazes in that example I showed you guys. This is an example of a 33x33 maze. This is something from the test set, right? So this is the training set. This is a problem from the test set. I have a lot of difficulty solving these 33 by 33 mazes, and actually the network has to produce the shortest path solution for it to be considered correct. And so even when I am able to solve these things, I'm never really confident that I get the shortest path. Also, these 33 by 33 mazes have the property that nearby starting and end pixels oftentimes result in long paths. So here's an example. This is the solution path for this problem. And this is a problem that our neural network is able to solve if it thinks for very many iterations. Right, so we're generalizing from these 9 by 9 mazes to these 33 by 33 mazes, and a system can actually make this generalization leap if it thinks for longer at test time. One of the interesting things about these systems is that they learn kind of unusual algorithms. So in this case, it's learned what appears to be, trying to interpret what goes on inside a neural network is hazardous, but what appears to be a subtractive algorithm where it starts by considering every possible location in the maze as a possible path to a solution, and then it lops off portions of that path as it thinks for longer. So you see there's big chunks of the maze here that are disappearing one after the other until finally everything disappears except the actual solution path for this particular maze. Okay, so the last application I want to talk about, we have this challenge problem. We like to solve something really difficult, and we'd like a problem where we can scale the difficulty of the problem without just scaling the size. So one might just say, okay, well, you're training on small problems and you're testing on big problems. Is that really a good, way to control difficulty? I actually do like that way of controlling difficulty, but we wanted something that would have more of a conventional human metric of difficulty that had been measured in some sort of scientific way. And so we looked at chess puzzles. So there's this online system called Lichess. It's an online chess server. It's quite popular. Actually, a number of my students that worked on this project were already big Lichess fans before we even did this. But Lichess, as people play, it will sometimes take snapshots of a chessboard from a human game, and then it will call it a chess puzzle. It calls it a chess puzzle if it can run a very powerful chess engine on it, and the chess engine is very confident that there's only one best move. And so the idea of a chess puzzle is you want to look at this game board, and then you want to try to identify what that best move is. Now, every chess puzzle has what's called an ELO rating. An ELO rating is a difficulty score given to it by playing against humans. So humans who play Lichess, they have their own ELO scores. A low ELO score is a weak player, and a high ELO score is a strong player. And by playing, they get scored by playing on these servers. And the way that you ELO score a puzzle is like the way you'd ELO score a human being. You show a puzzle to a really strong chess player, and if they succeed, then you boost the ELO score of the puzzle. So if they fail, then you boost the ELO score of the puzzle because a strong player couldn't beat it. And if you show it to a weak player and the weak player succeeds, then you push down the ELO score of the puzzle because it's a weak player can solve it. And so we end up with these ELO scores that basically rank all the puzzles from easy to hard. So what we do is we take 1 million puzzles from the Lichess database, and we sort them from easy to hard by using these ELO scores that were given basically by this human experiment. And I'm going to take the first 600,000 puzzles to be training data, and I'll take the last 200,000 to be test data. So these are the easy puzzles we're going to train on, and then these are the hard puzzles that we're going to test on. And there's a domain shift between them. And what we found in our original paper is that a feed-forward network trained on these systems can never seem to do better than 63%. A recurrent model trained on these systems can do considerably better. And interestingly, if we then let it think for longer, so we let it think outside of its training domain, then it can actually solve more difficult puzzles than it was able to solve if you run it for the 20 iterations that it trained on. We recently been able to improve this behavior. So our current systems are now able to get up to over 82% on hard puzzles. So keep in mind they trained only on easy puzzles. This is testing on hard puzzles, and you'll see that as you let them think for longer, so this is going from 20 to 70 iterations, there's this nice continuous improvement in performance. It's able to solve more and more hard chess puzzles as you let it think for longer and extrapolate the strategies that it learned outside of the training domain. Here's a simple example of a puzzle that it solves, and this is kind of breaking down the thinking process. So here's a chessboard. The black player is moving next. The black player is going to take this rook and it's going to attack this white rook. That's the solution to the problem. But there are other moves on the board. There's one other attack move on the board that sort of stands out, and that's to move this queen. I could actually take this queen and I could move it to this position, and that would put the white king in check. So there's a situation where I can create a check. So if I look at the output of the first iteration, it's just highlighting all of the pieces on the board. And by the way, the goal of these chess systems is to highlight the starting and the ending location for the optimal move. So I let it think for a while, and after 15 iterations, there's a sort of a red blob here, and there's a yellow blob here. And what is happening is it's identifying that it should move this rook down to this position. But you'll notice there's also these other purple blobs here. So looking at this, it's also considering moving the queen from this purple position to this purple position. So it's considering whether or not it should attack with the queen or whether it should attack with the rook. For various reasons, it turns out to be better to attack with the rook. And so we let the system think for longer, and then eventually the queen, the confidence in these queen locations fades away, and the network becomes extremely confident that it's going to attack with the rook. So we see that the position of these rooks becomes as confidence close to 1, and everything else fades away close to 0. Okay, so some final thoughts about thinking. There's some interesting things about these thinking systems that I find to be intriguing. Interestingly, thinking systems generalize to hard problems that lie outside of the training distribution. So in the conventional theory of machine learning, you train on a probability distribution, and then you test on the same distribution. And you say that generalizations occurred if you can solve more problems from the same distribution. Interestingly, these thinking systems, if you train on one distribution for, say, 20 iterations, and then you test on a completely different distribution of hard problems, feed-forward models will fail to make that distribution leap because of the domain shift. Recurrent models also fail to make that distribution leap. They fail under the domain shift. But then when you continue to run them, so if you let them think for longer than they did during training, they will then extrapolate, and suddenly they're able to tolerate these huge domain shifts. And you can generalize from, say, 9x9 mazes to 33x33 mazes, which require you to aggregate much more complicated global information. And it can make that generalization leap, but only if you let it think for longer. And so in some sense, it feels like these kinds of generalization behaviors lie outside of a conventional machine learning theory, because we're testing on such a different distribution than the trained distribution, and that distribution shift will break conventional machine learning systems. Another interesting thing is that thinking systems see only a problem and a solution. So there are different kinds of recurrent model trainings. An example would be something like neural Turing machine models, where you have a bit sequence, and then you instruct the model step by step how to reproduce the output bit sequence, but you give it incremental training input. So you say, okay, here's step 1, here's step 2, here's step 3. And by supervising every step of the algorithm, it can eventually learn an algorithm. What's interesting about these thinking systems is that we don't supervise the steps of the algorithm. They only see the problem and the solution. So they only see an input chessboard and the best possible move. And yet they're able to synthesize a scalable algorithm end to end without any supervision on what the steps of that algorithm should be. And that also gives us some insight about maybe why parameter sharing works. There's certain situations where sharing parameters between layers improves performance. Maybe it's because it generates these sorts of algorithmic behaviors. And then another final thought is that it might be possible, this is a bit ambitious, but it might be possible that thinking systems can potentially replace handcrafted algorithms. They can replace the handcrafted algorithms that are part of ML systems. So an example of that is game playing systems. An example of this would be something like AlphaGo or Mu0, which is a general game playing system. These systems actually make all of their planning and decision-making strategies with a handcrafted Monte Carlo tree search. Machine learning is only used to prune the tree and make decisions about which branches seem weak enough that you can chop them off. So we basically make planning into a classification problem. But all of the actual planning and strategy is done by a handcrafted algorithm. And so an interesting question is, given that machines seem to be able to learn these sorts of algorithmic behaviors end to end, so rather than using a tree search to solve your maze, you can learn a scalable search algorithm end to end. Right? You can learn a scalable search algorithm for chess end to end without having to handcraft the strategy generating components of that algorithm. Maybe it's possible to replace some of these handcrafted algorithms that we have in board game systems today with an end-to-end learned machine learning system. Okay, and then finally, here's a list of papers that I spoke about. Thank you very much for taking the time to listen, and thank you guys very much for inviting me. I wish I could have been there in person this time around. I've been to the Isaac Newton Institute before, and it's always been great. And my hope is that next time there's a great workshop like this, I'll be able to be there in person. Thanks, guys.
Thanks a lot, Tom. Would have been great to have you here personally, but thank you so much for the really interesting talk, which had some quite intriguing statements. Can I just ask before we go to questions for you, Tom, Lorenzo, how much under time pressure are you? Can we do 5 minutes of questions for Tom, or should we start with your talk and then do questions later?
It's okay. If I start to starve, I'll let you know, but I'm okay now.
Okay, thank you. Thanks to both of you for being so flexible. All right, other questions? Yes, Yuri.
Thank you very much for a very intriguing talk. I was wondering, did you think about applying these systems to problems like protein folding, where it's easy to predict how a small protein folds, but then hard to—
Yeah, so we're kind of in a process now where we want to start biting off more complex problems, and protein folding is actually on our list, and we've started poking around and speaking to some people about this, because actually I think this is like the protein folding is the ideal application of this sort of thing, right? You'd like to go to train on one set of molecules and then generalize to other molecules outside of the training distribution. I think that's a great application, but we've just started poking around and thinking about that, and if you have any concrete ideas or experience with that, please let me know. I'd love to hear from you about it.
Thank you so much.
Are there other questions? Can we do Mike and then you? Okay.
Hi, Tom. So thanks for the talk. I really liked your adversarial attacks, but they seem to be, one would assume they're tailored to a type of neural network. And you're arguing here later that recurrent neural networks structures are better. Do the recurrent neural networks, are they less prone to the adversarial attacks that you're generating?
That's interesting. So all of the attacks on the unlearned, you're talking about the unlearnable data set, right?
Yeah.
The stuff that we've experimented with so far has mostly been COMNETs. And I actually think that's the biggest weakness of that work. We have tested it on MLPs, and it does seem to work pretty well on MLPs. But there is more, there's no theoretical guarantees of security with these kinds of methods. And so if we're going to make empirical claims, I think it's important that they be tested very thoroughly. And right now, I don't think these systems have been tested thoroughly enough that I would recommend deploying them. But I think that with future research, I think that they might be. And the biggest, like I said, the biggest weakness is we need to test on more architectures. We haven't tested on feed-forward architectures. To me, the actual biggest weakness is we haven't tested on VITs. So we haven't tested on transformer architectures. And so for COMNETs, it's clear that the adversarial behavior transfers really well across architectures, but that doesn't mean it transfers to things that are totally different, like transformers and recurrent networks and things like this. So I guess the answer is, if your question does it work on feed-forward nets, the answer is I don't know. We haven't tried that yet, but that's like on our coming up on our menu of things to do next.
But I mean, given that you've by construction, it's the adversarial attacks don't fool biological neural networks, i.e. humans. That suggests there are networks out there that it won't challenge.
Yeah, and interestingly, so we've done some research where it seems like we can create adversarial examples in some sense that fool humans. It's debatable what counts as an adversarial example in that case, because some people sort of colloquially define an adversarial example as something that fools a machine but not a human. We can create small perturbations that seem to fool humans pretty well, and oftentimes not computers. But yeah, this work seems to be sort of exploiting. We actually use very weak adversarial examples, so we don't ensemble over different networks. We don't try to fool an ensemble of networks, because if you do that, you get this sort of generative behavior where the adversarial examples also start to generate features that a human would recognize. And so we've actually chosen to do very weak adversarial attacks because it creates very small perturbations that a human will not recognize. And strangely, that seems to be enough to break the training process. I'd also just point out that this is really different than conventional adversarial examples. Conventional adversarial examples, your network is already trained and you want a transferable attack that will break the network at test time. It takes very weak adversarial examples to break the network at train time, and they seem to be much more transferable than these sort of test time adversarial examples.
One more question.
Thank you very much for the talk. Very interesting. I wanted to ask you about in terms of recurrent models, is there a convergence that you've experienced in terms of iteration? So do the models kind of converge to some sort of a solution? Or
Right.
they
So,
overthink it, so to say?
Yeah, that's a great question. So it's the question to rephrase that is there a fixed point? I don't see any reason why there should be a fixed point if you take your sort of conventional like linear models type, thought about this. You should converge to like an eigenvalue of an eigenvector of the network in some sense, right? Our early architectures, this is one of our earlier results, they go up and then if you run them for a long time, they actually decompensate and performance goes down. And we call that the overthinking problem. And the work we're working on now is actually trying to solve this overthinking problem and create networks that have a better fixed point. And that's how we got to these improved results here. So like basically just trying to do architecture search and provide better architectures that will not suffer from overthinking. So for example, on mazes, we can now run for 1 to 2,000 iterations, train with 20 iterations, run for 1 to 2,000 iterations before it starts to overthink and decompensate. It does appear though, at least for the harder problems that we're solving, that you don't reach a fixed point and stay there forever. If we iterate for long enough, you kind of reach a decision and slow down. If you iterate for long enough, the system will eventually decompensate. And so is there a fixed point? It's really difficult to say. I actually don't see any theoretical reason why there should be a fixed point, but and empirically we don't observe a fixed point in a strict sense. But the name of the game, at least for our research right now, is trying to solve this overthinking problem and get that fixed point behavior to be as stable as we possibly can. And so right now I'd say we can get it to be pretty stable. I just don't know how to answer the question of whether there's actually a fixed point, because we can get it to slow down and stabilize pretty well for a few hundred iterations, and then eventually it decompensates. And so whether that's a fixed point, I don't know. I would like it to have a fixed point, and we're working very hard to get that fixed point behavior to be as reliable as possible.
Thank you.
Super. Thank you so much, Tom. I think in the interest of time, we are going